In this lesson, we're going to take a look at how we deal with forces when they act in multiple directions simultaneously. So we've looked at forces that are perpendicular to each other, and we know how to deal with that, but now we're going to actually deal with forces acting in two dimensions. So let's say I have an object, and it's resting on the ground, and somebody comes along and pulls on it, but instead of pulling on it horizontally, they pull on it at an angle, and we'll go ahead and say that this is angle theta. That means that this force has components, right? The applied force has a component in the x direction, horizontally, and another force in the y direction, vertically. Now, we can't forget that there's also two other forces that are acting, maybe three other forces that are acting on this box, right? There will be the force due to gravity pulling down on it, and then there's the normal force from the surface pushing up on it, and if it starts to move or it's trying to be put in motion, then there's a frictional force over here. Depending on if it's sliding or if it's trying to slide, it could be static or kinetic friction. Now, in the past, we've said that the normal force and the gravitational force add up to zero. Those two forces balance because they were the only forces in the y direction and it did not accelerate in the y direction. But that's no longer the case. This force now has a component in the y direction. It pulls up on that block a little bit. So when we deal with this case, the net force in the y direction is given by the normal force plus the force of the applied force in the y direction, or the y component of that force, plus the force due to gravity, and that equals mass times acceleration. Now, we are still going to assume that we're not picking this up off the ground. It's going to accelerate horizontally, but its acceleration in y then is still zero. So I can go ahead and write that my acceleration in y is zero, and that's what that is. That's a y acceleration because we're in the y direction. In the x direction, the net force in x is equal to the applied force in x, which is Fx, and minus the frictional force, or plus the negative of Ff, and that equals mass times acceleration in the x direction, right? So we just applied Newton's second law to both directions, and we've done this before, but we have this extra force now because this force is applied at an angle. And so now it's just a matter of solving, same way we always did, plugging in what we know to figure out what we want to know. In this case, if I wanted to know the acceleration on the block, I could do that. So the trick was recognizing that the normal force is going to be reduced because the y force is actually supporting some of the weight and the ground doesn't have to support it all. So how do I get this component? Well, Fx is the adjacent side, so Fx is equal to the applied force times the cosine of the angle, and Fy is equal to the applied force times the sine of the angle. And so I can make those substitutions, and so Fn plus F sine theta, and then plus Fg, but Fg is equal to the force due to gravity, mass times the acceleration due to gravity, but since I've made positive up, g is negative, so plus m times negative g equals mass times the acceleration in the y direction. Same thing over here, Fx becomes F cosine theta, and then plus, okay, now I've got to be careful because Ff, the frictional force, if it's sliding or kinetic, doesn't really matter, so we'll use coefficient of friction, we'll just say mu, we won't subscript it. Well, our normal force we used to say was Fg, but we can't do that anymore. Our normal force here, Fn, is equal to mass times the acceleration in y, which we're going to call 0, plus m times g, right, because if I add that over, minus F sine theta. And so we can see our normal force has actually been reduced by F sine theta, or the y component of that. So when we find our frictional force, Ff, which is equal to Fn times the coefficient of friction, we have to use this expression for Fn. We can't just use mg. So our frictional force is equal to mg minus F sine theta times the coefficient of friction. And so over here I can put that in, plus mg minus F sine theta times the coefficient of friction equals mass times acceleration in x. And so we can see that pulling at this angle reduces the frictional force, but it also makes the force less effective in accelerating horizontally since some of that force is used vertically. So it does change a lot of the problem when this force is at an angle.